Okay, so in our quiz, I said you could do 2 out of 4. I'm going to do all 4, of course. But you can. When I do these reviews of these quiz conclusions, I hope you actually go look at it and compare your own work with it, right? This is where you learn and where you can see what it should have been. All right, so the first one, so this one. I already told you factorial, don't hesitate. You almost always you're gonna have to do ratio test. There is one thing you could mention here is you could say, oh, it's an alternating series because of this minus, right? So because this can be written as minus 1 to the n, 4 to the n, which makes it more clear that it is an alternating series. And then you could perhaps think of the alternating series test, although when it involves factorials, that actually is a hard test. So another reason to try to ratio test. Okay, so one, I'm going to do the ratio test. Now, you have to make sure that you do this correctly, right? So we have to do the limit for n going to infinity. Their absolute values, which in this case just means that this part here is not necessary. So I'm not even going to write it anymore, so I'm going to actually really take absolute values here. So then we have this. Now on top comes the same expression where the n's are replaced by n plus 1. So we get this, okay? And then we have to simplify. The absolute values are not, signs are not even necessary, so I'm going to not write them anymore. This 4n plus 1 is on top. This n plus 1 factorial is in the bottom. 4n here, n factorial there. And then the trick here is to write the biggest factorial in terms of the smallest. So 1 plus n factorial is, you go all the way up to n. That's not the whole thing. You have to do one more factor, that is n plus 1. Okay, so, and of course the 4's also cancel, so we get a complete cancellation here and a single 4 left. So we get 4 n factorial, oh, this is still a limit, sorry, limit for n going to infinity, over n factorial times n plus 1, factorials cancel, now we get 4 over infinity, that is 0, so this means convergent. Why? Well, when in a test like this, every single detail, please make sure that you write it. So what I should write here is, it's not because it's 0 that it's convergent, it is because it's less than 1 that is convergent. Okay? All right, that's the first one. So the next one, this one, I wrote it in this way, in the hopes that you would better see what's going on, but let's think a little bit about what it could be. If you can also rewrite this as with the negative exponent back into the denominator, and then you could argue, well, this is a p-series, right? It's a polynomial. This is an exponential series, so a geometric series. But that's a mixed term, and mixed terms we normally don't know what to do with. We cannot limit comparison them with them. You might be tempted to do the ratio test, and in this case it would be a very difficult test a little bit because of this n to the 4th here. Remember, in the ratio test, n has to be replaced by n plus 1. And so this is going to be a rather complicated expression. It is possible, and some of you might have done this, but there's a better test here. It is, although it's not the first test I would think about, I just think, well, if I think of this as x cubed e to the minus x to the 4th, this is something that I can integrate. Because, with what? Not integration by parts. Because, why not? Because then it should be a simple power of x here. Perhaps 2x, perhaps minus 5x, but that's it. Not x to the 4th. But what it is that the thing that I just boxed is actually the derivative of that is x cubed. And that makes me think of substitution. So, long story short, number 2, we're going to solve. I'm saying a ratio test can work here, but the simplest one would have been the integral test here. So what we need to do is we have to integrate from, it goes from 1 to infinity, I guess, from 1 to infinity. Although this bottom endpoint never matters, right? I hope that by now you have understood why this doesn't matter really. So this is the function, right? I already have written it out here. This is always a limit. That's the first thing you have to do because it's an improper integral because of this guy. Okay, so 1 to t x cubed e to the minus x to the 4th dx. With the improper integrals, when you do substitution or any of these methods, it's sometimes much as better to first do the indefinite integral first. Otherwise, this limit, you have to keep writing limit, or you forget to write limit, etc. So let's do this. So this is the guy that I have to enter derive. And I have already, the reason that I'm even thinking about this is because if I take this for u, then du is minus 4x cubed dx. And that is exactly what I've left here. So this, where am I going here? I'm meant to go this way, right? These two guys together, that's there, well, up to -4, so perhaps we can do it this way. So now it's really the same, and so this becomes then, this whole thing is du over -4, the orange part, and then what is left is an e to the minus x to the 4th, but minus x to the 4th is u, so this. So minus 1/4, and the antiderivative, I'll write it one more time. The antiderivative of the exponential is just the exponential, okay? And now what we have to do, we have to plug in, don't forget this, plug back in the original function, minus x to the 4th. Plus c, but we are not interested in the indefinite integral, we are interested in this guy. So this is now the limit for t going to infinity of minus 1/4 e to the minus x to the 4th between 1 and t. So if I plug in that, I get limit of, for t going to infinity, minus 1/4 e to the minus t to the 4th minus, so plus 1/4 e to the power 0, which is just 1. Right, that's right, that way. Now what happens here? Well, this is the only crucial thing here. Now, because the negative exponent, if you can perhaps better see this, it is actually this one, right? It's actually e to the t to the 4th here. So now if I plug infinity, this becomes infinity. So this becomes minus 1/4 infinity. That doesn't matter, minus 1 infinity, that is going to be 0. So this is 0, and then we have here plus 1/4. Now what is matters is that this is not 0 infinity. That is not infinity. For an integral, an improper integral to be convergent, you have to get a real number here. So since this is convergent, the conclusion is this is convergent too. The first one, by the way, was also convergent, right? We said that already. Okay, what about number 3? Number 3, there should be no doubt here. We have powers on top and radical powers on bottom, so p series. It's not a p series, we have to do limit comparison. So the moment it's not a p series, even if it's just a single +1 or something, please do the steps. Okay, so some of you in the homeworks kind of very quickly look at the highest degree and then say, this is what it is. But no, show all the steps. Okay, so number 3, I think I'm going to have to copy it, right? So let me see, I have a version here. Okay, so sorry, summation 5n plus 2n squared plus 1 over the 4th power of n to the 13 plus 2n to the 7th plus 1. I got that right? Not double checking here. Yeah. Oh, there's a plus, but there's a minus here. Sorry, there's a minus. Right. I just that is not going to make a difference, but I just want to have the same thing. Otherwise, you're going to scream and yell. Okay, here we are. Okay. So what do we do? Well, limit comparison test. The limit comparison test. The first thing we need to do is to build. Step 1, if you want, is to choose what are we comparing it with. And the way that we do this is by looking at the highest degree terms in both. Now, it's not the first term, right? This is going to be the highest degree term, so don't let yourself be fooled there, n squared. And here the highest degree is, well, not 13 because it's the 4th power. So it's the 4th root of n to the 13. This is Bn. And I don't simplify because now in step 2, I have to calculate the limit for n going to infinity. So this is what we call an, and then this is what we have to calculate, right? And now we have to show that this is not 0 of infinity, remember. Okay, so what is this? And the way we always work this out is we take the tops and divide them, the top of an, that is this guy, divided by the top of bn, that's this guy, okay? And in bottom now we do the same thing. We get a fourth root of n to the 13 to n to the 7 plus 1 divided by the fourth root of n to the 13. Okay, then we do this, then we can now actually carry out this division term by term. So 5 over n plus 2 plus 1 over n squared. And in the bottom, so what we do is, I'm going to do it in one step, is I'll show it here. A fourth root over divided by a fourth root that we can combine it into a single fourth root. So I can think of this actually as a big fourth root of the whole thing. Okay, so we get down. So in other words, what I mean to say is we have this now. And so we divide now by n to the 10 is 1 minus 2 over n to the 6th plus 1 over n to the 13th. If we put, since n is infinity, there's an infinity here, I don't know what happened. That's a 0, that's a 0, that's a 0, that's a 0 if I plug infinity. So I've left of 2 over 1. And the only thing as we said is that it should not be 0 nor infinity. Okay, so that's not this is not means nothing. This doesn't mean convergent. No, what we need to do now is take a closer look at Bn. So where is Bn again? So now we're going to write it as well, let me write it first in rational powers. This is sometimes where people go wrong. The fourth root, it becomes this, right? Then I have to compare it with the p-series, and the strange thing about p-series is that they have their exponent in the denominator. So we do this. So p is 13/4 minus 2, which is 13/4 minus 8/4, which is 5/4. This is still bigger than 1, and that means convergent. So that this one was also convergent. Where did it go? Hey, I lost mine. That's weird. Okay. I must have accidentally done something and then it erased it. Okay, that's not no big deal. I'll copy the last one. So was the last question was summation minus 1 to the n ln over n squared, right? So now why did this disappear? Give me a sec. I don't want to do the wrong one here. I think this is it, but just double checking. Okay, what is this? This is the. No, it's not this one. It's this one. Yes. Okay, that's it. And this is for n going from 1 to infinity. Not that that matters much. So here we have a bit of options. We could, no, again, I say a bit of option, I shouldn't say that. The fact that it is a log n and n square makes me doubt that I want to do comparison, because logs cannot be compared, as well as ratio test. I told you logs are not very good with ratio tests. That's a strange thing with logs. So if it, I shouldn't say that ratio doesn't work with logs. Sometimes it does, but if it's just logs and powers of n, then the problem is going to be that if you do the ratio test with this thing, your limit that you're going to get is actually equal to 1, which is the only case you don't want, because it's the case that you don't know what happens. So there's an option here. I could do integral test. Doing that, I would prove absolute convergence, because in the integral test, I have to ignore this part. Like in the integral test, the numbers have to be positive. For one thing, minus 1 to the power x does not even exist as a function. Which can be, it's good to do that. If it works, it works. If you get convergent, then I conclude that this is convergent. But suppose you get divergent in using the integral test. You did all this work and you still don't know anything yet, because what you're trying to do was without a negative sign. And okay, if it does, it might not work without a negative sign. So if you're in a case like this, and this doesn't look too bad to take a limit of, I would do immediately alternating series test. I mean, I'm making a long excursion here, which probably everybody has already immediately saw that this was the alternating series test. But I just want to contrast it with the first one. The reason that I didn't do here, so sorry, it was this one, right? It was, or let me write it how I broke it down. It was, that was the one, right? Yeah, sorry, it has disappeared. But why did I not do the alternating series test, although it was alternating? Because of the factorials. They are very hard to deal with when you do limits. But here we are dealing with rather simple things. Let's see. For the limit, for alternating series tests, so of course then what we need to do is get rid of that -1. One thing one should prove, but I'm never going to ask you to do that, is that this is a decreasing function, because the weightings are, it will always work. So, all right. Now the only problem here is, of course, if I plug infinity, I get infinity of infinity. But we are known what we know what to do with that, right? And we are exactly in a fraction here that is of one of the L'Hopital forms. So I'm going to take, first of all, I should now think of these as functions of x, so of a real variable, so that, because I have to take derivatives. So the L'Hopital now says, take derivative of the top, that is 1 over x, take derivative of the bottom, 2x, and that's it. It's not a quotient rule, but please do not confuse those two. Okay, now be careful if, well, don't be careful. You don't need to be careful here. If I bring infinity, the top is 0 and the bottom is, infinity in the bottom is also 0, but it is nicer to put, always when you have things like with various x's, powers and x in here, let's all write them together. Like for instance here in the denominator. And now it's clear that it's 1 over infinity is 0. Now that is what we need to see for an alternating series test. So this is conversion 2. Okay? So the test was very simple, right? If it was always convergent. But the whole point is, of course, to show all the details.